Ladies and gentlemen, you have learned how to integrate using U substitution, a wonderful, wonderful rule that's going to help you in many ways. But have you ever noticed something? When you look at each of these, have you noticed yet that in every problem you've been doing, it just happens to work out perfectly? When you look at the three examples up on the board, what I want you to do is think to yourself, what would I substitute in for U? If these are the values that you came up with, good job, you're doing well. And then have you happen to notice what the derivatives of these might be? I mean, come on, folks. Is it a coincidence? Why is it that when your derivative is 8x, there always happens to be exactly 1x, which when you substitute in, will divide out? Or when you don't have an x at all, there's no extra x's there. Is it just always going to be that whenever I have x to the 10th inside a function, I'll have x to the 9th right next to it so that when I substitute, it all works out beautifully? Well, so far up to this point, it has always worked out beautifully for you. It has not taken into account some of the possibilities here. What if this value here had actually been x squared? Or what if this had been, instead of just 9, 9x? Or what happens if this really doesn't happen to be x to the 9th, it's x to the 8th? And each of these situations, this kind of throws a monkey wrench into our plans just a little bit. And some of them you're not really going to be able to solve using this next rule that I gave you. In fact, for some of these rules, I dare say for that third one, there might not be a specific rule for this situation. It might be that you have to use a type of estimation, like a Riemann sum. But here is how you can do a second substitution to make this work out. Now, I don't think any of your professors in college are going to call it dub sub, but that's what I affectionately call it. It just means we're going to substitute not once, but twice. You figured out that U was equal to 9x plus 7. And, of course, because of that, we do have, sort of a second substitution, but really it stems from the same thing. Well, actually, we're going to do something similar here. If U is equal to 9x plus 7, what happens if I subtract 7 from both the left and the right-hand sides? What happens if I divide each side by 9? I have a second equation here, and that is that x is equal to U minus 7 divided by 9. How does that help us? Well, let me explain. If I substitute in for U and I substitute in for dx, just like I normally would, I'm going to have some 9s divide out. I can rewrite that square root as a negative, but I still have an extra x there. This won't do. I'm integrating with respect to U. I have a U term, but that doesn't have any U's. It's a second variable, which is going to be problematic. So what I'm going to do is I'm going to go ahead and substitute that a second time. X is equal to U minus 7 over 9. Now, if you'll give me a minute, this is going to work out much nicer. So once I've substituted in that 1/9, that's bothering me. I'm just going to move it out front. But I take the U minus 7 times U to the negative 1/2, and I'm not integrating yet. I'm just rewriting or simplifying. Then I can integrate U to the 1/2, and I can integrate U to the negative 1/2. And don't forget, in that final step, make sure you remember what U was equal to originally and back substitute. So dub sub is something that you can use when your variables don't always exactly match up with U and dx. When you substitute U and dx in, and there still might be an extra 1 or 2 x's lying around. If there are, solve for x, do a second substitution, and then algebraically manipulate it before integrating. That will give you a better answer.